about stability of isolated vacuum systems in general relativistic kinetic theory. Please.
Okay, thank you very much. So I'd like to thank the organizers for the invitation to speak. I'm sorry that this conference couldn't go ahead in person, but it's a great pleasure to speak nonetheless. So I'm interested in general relativity, and in general relativity, collisionless kinetic theory is governed by the Einstein Vlasov system. So I'll begin by introducing this system. Then I actually have not written a paper in kinetic theory for a few years now. So I'll talk about some slightly older theorems which concern the stability of the trivial solution to this theorem, to this system. And then at the end, if there's time, I'll talk about a more recent result, which is about the stability of a non-trivial family of solutions, namely the Schwarzschild family of black hole solutions for the vacuum Einstein equations. So in this language, vacuum Einstein equations means Einstein Vlasov, but where you set the Vlasov part of the solution equal to 0. So this is not a result in kinetic theory, but I hope it will be of interest to this audience nonetheless. And one can certainly motivate this by problems in kinetic theory. So Einstein Vlasov models a collection of particles in which collisions are sufficiently rare so as to be neglected, and which interact with each other only via gravity as described by general relativity. So there's a wide range of situations which this is often used to model. Some examples are, so the Einstein massless Vlasov system, which I'll introduce in a moment, is used a lot to model clouds of neutrino radiation. Moreover, this system describes galaxies, in which case each star in the galaxy is treated as a particle. This is also used a lot in cosmology, in which case the galaxies themselves are treated as particles. And there are two types of questions that we're interested in addressing. The first is the question of when solutions exist globally. And the second is whether we can describe the asymptotic behavior of solutions as some appropriate notion of time goes to infinity. And of course, in relativity, time is a relative notion. So one has to just be a bit careful about what one means exactly by these two things, and I'll return to that point later. So the simplest regime in which to address these questions is regimes close to certain explicit stationary solutions. And so this will be the setting of everything that I'll say. I'll further consider the stationary solutions that I'll consider will always be isolated self-gravitating systems, meaning that the spatial domain will be something unconfined like R3, for example, and the fields will have good decay properties as one goes to infinity in R3. And the stationary solutions will also be vacuum, meaning that there'll be no particles at all present in the stationary solutions around which one perturbs. So I will show you the system in a moment. However, some of the system can be a lot to digest if you're seeing it for the first time, and some of the concepts are easier introduced by way of equations, which I hope are more familiar to this audience. So I'll discuss two such equations before I go to Einstein Vlasov. The first is the Vlasov-Poisson system, which is the Newtonian analog of the Einstein Vlasov system. So the unknowns are a particle density function f, and again the spatial domain is R3. And the other unknown is a gravitational potential, which I'll call phi. So F satisfies a Vlasov equation. Here, whenever you see a repeated Latin index, there's a summation over I equals 1, 2, 3. And this couples to the Poisson equation satisfied by phi. So the coupling enters through this rho on the right-hand side, which is defined to be this average of F. And for simplicity, I'll only consider a single species of particles and make the assumption that all of those particles have equal mass. And I've included the mass parameter m here in the equation. So m for in this case is some strictly positive number. So one silly observation about this system is that the vacuum Poisson equation is trivial. So if one looks at the Poisson equation and sets rho on the right-hand side equal to 0, this equation we better know by the name Laplace equation, but for reasons which will become apparent momentarily, I'll call this the vacuum Poisson equation. And of course, together with these boundary conditions at infinity, the only solution of this equation is the zero solution. So actually F completely determines phi. And so the trivial solution of this system is F equals 0. And by this remark, this means that phi itself has to, of course, be 0 as well. So the simplest regime in which to study dynamics of this equation is that in a neighborhood of the zero solution. And this was first studied in a pioneering work of Bardos de Gonde, all the way back in 1985. So they show that the zero solution is globally nonlinearly stable. So if F is initially small in some appropriate norm, then the corresponding solution exists globally and disperses. So the proof of this theorem by today's standards is not so involved, and the reason is the Poisson equation. If you view this rho on the right hand side as fixed, this is a reasonably simple equation. So it's elliptic, it's linear, and moreover there's quite a simple representation formula for solutions. So the proof is based on L infinity estimates for the characteristics of the Vlasov equation and their derivatives, together with the representation formula for the Poisson equation. And in fact, this proof closes without, you can close this proof without having such detailed information about the behavior of the solutions. So this problem since then has been revisited by many people, using different techniques and obtaining more and more detailed information about the solutions. So the second equation I'd like to discuss is the Vlasov-Maxwell system, which describes a cloud of charged particles. So the unknowns are F again, and now also E vector fields E and B, which describe the electric and magnetic fields. So F again solves a Vlasov equation, which now involves E and B, and E and B solve the Maxwell equations, which are now hyperbolic equations, and they're sourced by rho and J, which are again these averages of F. So rho and J are various P integrals of F. And now, so this is a relativistic equation. So now there is this P0 in the Vlasov equation, and P0 is a function of P together with M, which is the mass of the particles which are present. So M can either be strictly positive as before, or M can also be 0 in this case now, which means that the particles all travel at the speed of light, which is the characteristic speed of the Maxwell equations. And the system, it behaves qualitatively very differently depending on whether this mass is strictly positive, and we call that the massless case, or whether the mass is 0, and we refer to that as the massless case. So again, one can make this silly observation if one considers the vacuum Maxwell equations, so the Maxwell equations where we set rho and j on the right-hand side to be identically 0, then unlike the vacuum Poisson equation, there are non-trivial solutions to vacuum Maxwell equations. However, these are still relatively simple equations. So they're hyperbolic now rather than elliptic, but they're still linear, and there's still a representation formula for solutions. Moreover, there are non-trivial solutions. However, there are no solutions which decay at infinity, which are stationary, other than the 0 solution itself. So now, obviously, F does not completely determine E and B. So when we say trivial solution of Vlasov-Maxwell, we mean the F being the 0 function together with E and B being the 0 vector fields. And again, the simplest regime in which to study this equation is in a neighborhood of this trivial solution. And in the massive case, this was first done by Glassi and Strauss back in 1987, who proved the analog of the Bardos-de Gonne theorem. So again, the philosophy of the proof is similar. It's based on L infinity estimates for the characteristics together with the representation formula for the Maxwell equations. And again, this has been revisited by many people since then. I should say as well that there are a huge number of relevant references for this talk. Unfortunately, I will not be able to mention all of them, so I apologize in advance to anyone who I forget to mention. So that's the massive case. Surprisingly, I don't think the massless case had actually been addressed until very recently by Igor, who proves the analog of this theorem in his PhD thesis. And the methods are not based on Glassi, Strauss, or Bardos-de Gonne, but they're more similar to those I'll discuss in a moment. Okay, so the Einstein Vlasov system, on the surface, it looks similar. So the unknowns now are a particle density F again, and now the gravitational field is described by a Lorentzian metric G. Or if you prefer, you can think of G as a symmetric 4x4 matrix, which has at each point Lorentzian signature minus, plus, plus, plus. Or in other words, it has 1 negative eigenvalue and 3 positive eigenvalues. And you should think that the idea is that one of the directions is recognized as the time direction. So then F solves a homogeneous transport equation again. Now this involves these Christoffel symbols gamma, which schematically you can think of these as looking like first order derivatives of the metric G. Again, there's P0 in which the mass of the particle is considered featured features. And P0 is defined in terms of P and G and M via this relation. So here there's the repeated Greek indices indicate a summation over 0, 1, 2, and 3. So over the space and time components. So the Vlasov equation here, you should think just says that the characteristics of this equation are exactly the geodesics of the geodesic equations of the metric G. Then we have the field G solves the Einstein equations. So on the left is this object called the Ricci curvature of G, which I'll say a few words about in a moment. And on the right-hand side are components of the so-called energy momentum tensor T. So T involves an average of F again. This time it's a second moment of F, but similar to Vlasov-Poisson and Vlasov-Maxwell, it's an average of F, which is on the right-hand side of the field equation. So there's a lot of redundancy in the Einstein equations due to the geometric nature. So this Ricci curvature on the left-hand side is a geometric object. And strictly speaking, these equations don't take any particular type. However, you should think that Ricci curvature is some sort of second order hyperbolic differential operator. And I guess the easiest way or the most direct way to see this is to consider a particular coordinate system, which are known as harmonic coordinates. And with respect to harmonic coordinates, whatever that means, the Ricci curvature takes the following form. So it's associated to G is this second order differential operator. And it's this differential operator applied to the components of G plus some nonlinearity, which depends on G and first order derivatives of G and is quadratic in the first order derivatives of G. So because G has Lorentzian signature, you should think that this operator is a hyperbolic operator. And in fact, this looks like some sort of nonlinear wave operator. So the trivial solution of this system is again F taken to be identically equal to 0. And the simplest example of a Lorentzian metric is the so-called Minkowski metric. So the simplest 4x4 matrix with signature minus plus 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 is that with minus 1, 1, 1, 1 down the diagonal. So we call that the Minkowski metric. And I'll refer to this solution as Minkowski space. So if G is equal to the Minkowski metric, then this operator just takes the form of the standard wave operator, which we're all familiar with. So indeed, you should think of this as a wave operator. And in fact, the Einstein equations around this trivial solution linearize to the standard linear wave equation for the perturbations. So I'd like to talk about two theorems for this system. The first is the stability of the trivial solution in the massless case when all the particles have zero mass. And this was actually the subject of my PhD thesis back in 2016 and has since been revisited using different approaches. And the second theorem is about the analogous result for the massive case when this mass is strictly positive. So this was shown independently in a joint work with Lindblad and independently by Feynman, Juju, Smolevici using a different technique. And in fact, both of these two problems, they simplify quite dramatically in spherical symmetry. And in spherical symmetry, they'd both been resolved much earlier. the massless case by Dafermos in 2006, and the massive case by Ryan and Rendell all the way back in 1992. So before talking about these theorems, I have to say a few words about the vacuum. So recall, vacuum Poisson equation with those boundary conditions was actually trivial. The vacuum Maxwell equations were admit non-trivial solutions, but they're not so difficult to understand. The vacuum Einstein equations, however, you should view as a supercritical system of nonlinear hyperbolic partial differential equations. So, for example, if one imposes this harmonic coordinate system, then they take this form of nonlinear wave equations, nonlinear system of wave equations for the components of the metric G. So, just showing stability of the trivial solution in the vacuum in the vacuum when F is identically 0. This was a very non-trivial problem due to the nonlinear interaction of gravitational waves. In particular, there's no representation formula for solutions of this system. Which in particular means that these theorems and the theorem in these theorems, they're necessarily based on they have to be based on a different approach to the Bardos-Degon approach for Vlasov-Poisson. So the stability of Minkowski space in vacuum was first shown in a monumental work of Christodoulou and Kleinemann in the early 90s, and since then there have been many further works, perhaps most notably by Lindblad Rodnianski in 2004. So this problem is very, very interesting. You should think the problem is actually critical to 3+1 dimensions. So it's a difficult theorem in 3+1 dimensions, but it's comparatively much easier in 4+1 dimensions and higher. And the reason for this is that one doesn't have to use any of the special properties of the Einstein equations in higher dimensions. So in other words, this theorem is true for the typical equation, or for example, it's true for this system for any nonlinearity f, which is quadratic in first order derivatives in 4+1 dimensions and higher. However, it's false in 3+1 dimensions for the typical equation. So the only reason that this is true in 3+1 dimensions for the vacuum Einstein equations is because there's some incredibly special structure in the nonlinearity, which was introduced by Kleinemann in 82 and is called the null condition. So the original proof of Christodoulou-Kleinemann, which is 500 pages long, this involves, it's not based on harmonic coordinates in which the equations take the form of a system of wave equations, but it's based on a more geometric formulation of the Einstein equations, in which some form of this good structure is present, and that good structure is heavily exploited. The Lindblad-Rodnianski proof, it is based on these harmonic coordinates, and they notice that it's based on the observation that, well, this very good structure of Kleinemann is not present, but there is still some good structure there, which is good enough to prove this theorem. So they call that the weak null condition. However, you should still think that this is something very non-generic. So this is structure which is not present in the typical equation. So unfortunately, I don't have time to go into all the details of those proofs. But just in order to motivate what I'd like to say about the theorems for Einstein Vlasov, let me just mention let me just very broadly mention the technique employed. So they're both based on a method called the vector field method, introduced by Kleinemann in the 80s. And in the vector field method, one commutes the Einstein equations with the following vector fields, and then proves L2-based energy estimates for various combinations of these vector fields applied to the solution. So these vector fields, they arise due to the fact that they generate symmetries of Minkowski space, and this means that they have good commutation properties with the wave equation. And the proofs are based on commuting and then proving energy estimates up to some order, which n, which in Lindblad-Rodnianski is something on the order of 10. It's a bit lower in the original Christodoulou-Kleinemann proof. And then, of course, this good structure has to be exploited crucially in order to control the nonlinear terms. So the new aspect, the main new aspect which arises in the coupling to the Vlasov equation, is to control combinations of these vector fields applied to these components of the energy momentum tensor, which you'll recall schematically they look like these averages of F. Okay, so before discussing how that works in the nonlinear problem, it's worth just making a few comments about the free transport equation. So free transport equation is like so this is the Vlasov equation on Minkowski space, the Vlasov equation with respect to that Minkowski background. So one would like to control these vector fields applied to these averages of F, which schematically they look like this. And they're controlled by controlling appropriate vector fields applied to F. And note that F lives upstairs, but the average lives downstairs. Okay, so these vector fields and this average, they involve only T and X. But F, of course, lives upstairs and depends on T, X, and P. So one commutes either the Vlasov equation or the associated characteristic system with vector fields. But of course, these vector fields are not the correct things to use because they only depend on T and X. They don't depend on P. So the correct vector fields to use to apply to F are these lifted vector fields, which involve also these P derivatives. So the bar here means that there's some sort of lift happened, and the M here stands for Minkowski space, the lifted vectors you would use on Minkowski space. Why exactly it's these things that you add, and why you add nothing to this final vector, there's a nice story behind this, but I don't have time to go into this now. Suffice it to say that there is a correct thing to do in Minkowski space, or there is a correct thing to do for the free transport equation. So now turn into the nonlinear problems. So first, in the massless case, the proof is based on the Christodoulou-Kleinemann proof, the more geometric proof. And the point is that this the problem in this massless case, it localizes to a semi-global quantitative Cauchy stability statement. So if for example one just considers the free transport equation in the massless case, and one assumes that F is initially supported inside some ball as depicted, then since all of the particles travel at the speed of light, they will all leave the center. They'll all leave the origin of R3 after some finite time. And in fact, the solutions will remain supported between these two depicted outgoing light cones. And so, using this observation, the nonlinear problem actually localizes to this quantitative local existence in Cauchy stability statement. So it's a local existence in this incoming retarded time u, which is t minus mod x. However, there's a semi-global aspect to this problem because the v length, so v is t plus mod x, is infinite. So it's a local problem in this incoming time, which is infinite in this infinite and uniform in this outgoing v time. So then the stability Minkowski space is a corollary of this quantitative theorem along with the Christodoulou-Kleinemann theorem in vacuum. And in fact, there's nothing so special about Minkowski space. One could similarly show that if one has a solution of Einstein massless Vlasov, which disperses appropriately and has similar support properties, then this should also be stable. So, as I say, the main step in this semi-global theorem is to control combinations of these Z applied to these averages of F. And how does one do this? Well, consider, for example, the characteristic system, and recall that the characteristics involve these Christoffel symbols gamma, which schematically look like the first order derivatives of G. So for the massless free transport equation, the characteristic system is the same, but with 0 on the right-hand side here. So one can try commuting this characteristic system with these vector fields, which worked well for the free transport equation, and then hoping that what appears on this right-hand side will decay sufficiently fast to just be treated as an error term. So of course, one has to integrate this right-hand side twice. So the hope would be that this right-hand side decays a rate which is strictly faster than 1 over s squared in order to be treated as an error. So if one is naive, then it does not look like this will decay sufficiently fast. However, the observation is that, well, the different components of the characteristics and the different components of these Christoffel symbols gamma, some will decay at faster rates than others. And there is some structure in this product. So the worst terms, the slowest decaying terms, will never appear multiplying the slowest decaying terms. So slowly decaying terms only ever actually appear in this product multiplying terms which decay fast. So in fact, exploiting this good structure, one sees that in fact this does decay a twice integrable rate, and indeed can be treated like an error. So there's some sort of null condition here in the Vlasov equation, and in this massless case, the argument that you would use for free transport can be used. However, one just has to exploit special structure in the error in order to be able to see that. So then, of course, one continues to higher orders and controls these in L2. In fact, in the proof, it's important actually to use not this characteristic system, but a more geometric formulation of the Vlasov equation, which involves introducing the so-called Sasaki metric on the tangent bundle of the solution manifold, and studying what's called the Jacobi equation of that metric. This involves this would require introducing a lot more geometry than I'm willing to do. So let me not talk about that here. So finally, the final comment about this is that the different components of the energy momentum tensor, which recall they were these second moment integrals of f, the different components decay at different rates, and it's actually important to exploit the fact that certain components decay faster than others. So there's null condition in the nonlinearity of the Einstein equations. There's null condition in the Vlasov equation, and there's also some sort of null condition here in this system as well, where these t components of t appear on the right hand side. Okay, so let me turn now to the proof in the massive case. So this is based on the Lindblad-Rodnianski proof in vacuum, and unlike in the massless case, where structure had to be exploited in the nonlinearity, the proof in this case can localize to the so-called interior region, where all of the components of gamma decay at the same rate. So there's no structure to exploit in this case in the Vlasov equation or in the characteristic equations. However, one can easily see that the sharpest rate that these Christoffel symbols should be expected to decay at is this critical rate of 1 over s squared. Okay, and this 1 over s squared is exactly critical for integrating twice. And indeed, this means that those vector fields that one would use in the case of the free transport equation, it means that they will actually grow logarithmically when applied to f. And if all one knows is the logarithmic growth of these vector fields applied to f, then this is insufficient for when one goes back to the Einstein equations. This is insufficient for recovering this 1 over s squared behavior of the components of the Christoffel symbols. So note again that this problem is critical to 3+1 dimensions again, but this is in a different way to it was for the wave equations, let's say. So from the nonlinearity in the Einstein equations. So this 1 over s squared, you should think the 2 is it's the spatial dimension minus 1. So when you go to higher dimensions, this power gets bigger and bigger. However, one still only has to integrate twice. So this is again critical to 3+1 dimensions. So the idea is to not use those vector fields that one would use in the case of the free transport operator, but the vector field should be better adapted to the geometry of the perturbations. So in what we wrote, there is a procedure for arriving at these vector fields, which they schematically look like this. So the vector fields from free transport plus some nonlinear correction, which schematically involves the integral of the Christoffel symbols along the characteristics all the way back to initial data. So to summarize that, in the massless case, the idea is to use the free transport argument and to exploit special structure in the nonlinear terms. In the massive case, the idea is not to exploit structure, but one has to non-linearly correct the free transport argument. So, okay, that's all I wanted to say about that. Let me now turn to this more recent theorem about the vacuum Einstein equations. So from now on, F is identically equal to 0. So recall that we talked about the vacuum Poisson equation, which is trivial. That only has one solution with the correct boundary behavior. The vacuum Maxwell equations were non-trivial, but recall we said that there are no stationary solutions which decay at infinity, other than the zero solution itself, other than E and B being identically 0. Now, this is not true anymore for the vacuum Einstein equations. There are non-trivial solutions with these good decay properties at infinity. And the most famous family of such solutions is the Schwarzschild family of static black holes. So this is a one-parameter family parameterized by this M. And G takes this form, or if you prefer this matrix notation, you can think that G is the diagonal matrix with these coefficients down the diagonal. And this family was actually discovered on the Eastern Front in 1915, and it was not understood until much, much later, however, that each member of this family describes a black hole, and this parameter M has the interpretation of the mass of that black hole. And for context, the name black hole actually was not introduced until the 60s. So what does it mean to say that this solution possesses a black hole? The definition is quite difficult to process in real time if you've never seen it before. So let me not say exactly what this means. I just want to emphasize the global nature of the definition, or to introduce a word which I'm about to use a lot, the teleological nature of the definition. So there's an asymptotic boundary called future null infinity, which can be attached to the Schwarzschild solution. And the causal past of that asymptotic boundary is not the entirety of the solution. Or in other words, there are regions of the Schwarzschild solution which cannot send signals to this asymptotic boundary, which you should think describes distant observers. So when this happens, we say that there's a black hole present. But note that it's not possible to just take some open subset of the solution and say there is a black hole here or there is not. One really needs the global solution so that one can attach this asymptotic boundary to make sense of this notion. And this fact is something which complicates the analysis of the theorem, which I'll describe, and I'll return to this point a bit later. So the black hole exterior of Schwarzschild, the region which can communicate with these distant observers, is given by r greater than 2m, and this region is complete, meaning that Schwarzschild exists globally as measured by observers at infinity. So recall notions like, since time is a relative notion, notions like global existence in time is also a relative notion, and Schwarzschild exists globally for some observers, but not for others. So we say the exterior region is complete to mean that you should think that this means the Schwarzschild solution exists globally as measured by observers from infinity. Then the boundary between the black hole exterior and the black hole interior is what's called an event horizon. And in Schwarzschild, this is located at r equals 2m. So r here is a polar coordinate on R3. Okay, so the first version of the theorem I'd like to discuss is this is joined with Dafermos, Holzegel, and Rodnianski. It's from last year. And it says that the exterior of the Schwarzschild solution, the black hole exterior of Schwarzschild, is nonlinearly asymptotically stable as a solution of the vacuum Einstein equations. Asymptotically stable meaning that small perturbations of Schwarzschild decay to another member of the Schwarzschild family. So in view of this statement about asymptotic stability, if you have any familiarity with this subject, you'll know that there's only one sense in which this theorem can possibly be true, and that's if it's true, if it's meant modulo the Kerr solution. So Schwarzschild is not the only stationary solution of the vacuum Einstein equations. It actually sits inside a larger family of stationary solutions called the Kerr family. So each member of the Kerr family describes a uniformly rotating black hole. And it's much more complicated. It was actually discovered much later in 1963. So I've included the expression here for completeness, but perhaps don't look so hard at it. The most important points are, well, first of all, none of these coefficients depend on time. So indeed, this is a stationary solution. Then recall Schwarzschild was a one-parameter family. There was only this mass parameter m. Kerr is a two-parameter family. There's the mass m again, and now there's also this angular momentum parameter a. And this still describes a black hole as long as a is not too large with respect to m. And if one sets a equal to 0 in this expression, then one gets exactly back the expression for the Schwarzschild metric, which I put on the previous slide. So one should think, I mean, Schwarzschild is a one-parameter family, Kerr is a two-parameter family. So it's tempting to view Schwarzschild as being codimension 1 inside the Kerr family. It's actually more convenient to view Schwarzschild as being codimension 3 inside the Kerr family. So you should think that if you have a member of the Schwarzschild family and you'd like to describe a nearby Kerr solution, one not only has to prescribe an angular momentum parameter A, but one also has to prescribe an axis around which the Kerr black hole is rotating. So the angular momentum parameter A together with the axis is 3 parameters in total. And so you should view Schwarzschild as being codimension 3 inside Kerr. And this number 3 will keep appearing, and it's always for this reason. But in any case, Kerr with small a is a small perturbation of Schwarzschild, and it's stationary, so it clearly doesn't converge to Schwarzschild. So when I say stability of Schwarzschild, I mean the full finite codimension nonlinear asymptotic stability of Schwarzschild. So the theorem can be more precisely stated as follows. So for all data which is close to Schwarzschild with some mass m initial, and moreover lies on a codimension 3 submanifold of the space of initial data. So you should think that Kerr does not lie on this codimension 3 submanifold, But moreover, you should think that any initial data that does not lie on this codimension 3 submanifold, the resulting solution will not converge to Schwarzschild, but it should converge to a member of the Kerr family with non-zero A. So it's in this sense that this is full finite codimension stability of Schwarzschild. So for all such data, the resulting solution possesses a complete future null infinity whose causal past is bounded to the future by a complete event horizon. So in other words, those qualitative properties of Schwarzschild, which I mentioned earlier, namely the fact that it contains a black hole and exists globally as measured by observers from infinity, these properties are shared by the perturbations. Secondly, the solution remains close to the Schwarzschild which was perturbed in the black hole exterior. And finally, the solution decays at an inverse polynomial rate to another member of the Schwarzschild family with a nearby mass. So again, you should think of the first of these points as the statement of global existence as measured by observers at infinity. And in relativity, this has a name. We call it the weak cosmic censorship conjecture, first formulated by Penrose. So it's weak cosmic censorship in the neighborhood of Schwarzschild. The second statement is a statement of orbital stability of Schwarzschild. And the third is asymptotic stability of Schwarzschild, all restricted to this codimension 3 hypersurface. So note that the presence of the Kerr family means that without this restriction to the codimension 3 hypersurface, this third point cannot possibly be true. But one can still expect the first 2 points to be true without that restriction. However, because of the supercritical nature of the nonlinearity in the Einstein equations, one actually cannot show any one of these 3 statements without actually, in fact, showing all 3 of them at the same time. So these 3 statements come as a package, and therefore asymptotic stability of Schwarzschild in this sense requires this restriction. So there's been a tremendous number of relevant previous works, particularly in the physics literature, dating all the way back to the 50s. In the mathematics community, there's been many works in recent years. This problem's been studied in symmetry classes. The simplest symmetry assumptions are those which reduce this to a 1 + 1 dimensional problem. And there's some older works on stability of Schwarzschild in those settings. Beyond restrictions to 1 + 1 dimensions, the problem becomes considerably more involved. There's a work of Kleinem and Jeftel on polarized axisymmetry from 2018. There's also a nice work of Hinz and Vaschi on stability of so-called Kerr de Sitter, which is the cousin of the Kerr family for the Einstein equations with what's called a positive cosmological constant. And there are many other works I don't have time to mention, unfortunately. Then, of course, it's important to generalize this result to Kerr in this full subextremal range where A is less than M. And one can begin with the very slowly rotating case. So one can begin with the case where A is very small, and there are many aspects of the Schwarzschild theory which can be perturbed in this case. So this is work in progress of several groups. In particular, there's a series of works by Georgi, Kleinem and Jeftel, and Shen. And some of those have appeared on the archive already. So let me also mention that there have been works related to Einstein Vlasov close to Schwarzschild and Kerr. So there have been constructions of stationary solutions close to Schwarzschild and Kerr with F, which is non-identically zero, so non-vacuum stationary solutions. There have been a number of works about the linear results for Vlasov equation on these fixed backgrounds. So, for example, in the massless case, there have been some works of Anderson, Blue, Juju, Bigorn. There's also a forthcoming work of Weissenbacher, who is a PhD student at Imperial. And there's also a nonlinear result forthcoming for the Einstein massless Vlasov system in spherical symmetry of Vlasov. So I guess I'm running out of time. I'd like to just end by making a few remarks about this Schwarzschild theorem. So I'll maybe end on this slide. So first, recall that the black hole exterior is characterized teleologically, meaning that just at the level of initial data, it's impossible to say exactly what's going to be in the black hole exterior and what's going to be in the interior. The only way to determine what the black hole exterior is to solve this problem globally and look at what's in the past of this asymptotic boundary. However, I only make any claims about this problem in the exterior. I'm not claiming anything about the black hole interior, where in fact instabilities are expected. So in this problem, not only is the solution an unknown, but the domain on which the solution lives is also an unknown in this problem, which has to be determined as part of the proof. So moreover, the coordinate system in which the solution decays to Schwarzschild in this familiar form, or in other words, the gauge in which the solution decays to Schwarzschild, this is also something which cannot be explicitly determined in terms of initial data, but this is also something which is teleologically determined. So the coordinate system has to be built as part of the proof, and this is also teleologically normalized to both the event horizon and to this asymptotic boundary future null infinity. And finally, and this is a nonlinear phenomena, and the first is a nonlinear phenomena as well. This codimension 3 submanifold is also characterized teleologically, meaning that the initial data that lie on this codimension 3 submanifold, they all contain exactly the amount of angular momentum initially, which they will radiate in evolution. And in generality, there is no way to determine how much angular momentum a solution is going to radiate until one solves the problem globally and sees. So this codimension 3 submanifold also has to be determined as part of the proof. So you should think the unknowns in this problem are not only the solution, but they're also the domain on which the solution lives, the coordinate system in which the solution exists globally, and moreover, the initial data is also an unknown in this problem. So I'm out of time, so I'll have to tell you on another occasion about how those difficulties are addressed. So thank you.
Thank you, Martin. So we have time for a few